Welcome back to today's Planet Earth, Our Loving Home on Supreme Master Television, where we are focusing on how the oceans affect the world's climate. Recently, scientists have discovered a fast-moving, deep ocean current around Antarctica that transports massive volumes of water annually and is a major component of the Great Ocean Conveyor.
An important part of this overturning circulation are these very strong deep currents that we find mostly on the western sides of the ocean basins. They're pretty well studied in the Atlantic, but we know very little about them in the Southern Ocean. And so there's a huge plateau, a submarine mountain range, which is more than 2,000 kilometers long, that sits in the Indian Ocean sector of the Southern Ocean. On the flanks of that, we had some reasons to expect there might be a current there, but no one had ever measured it. So we really didn't know just how strong the currents were and whether it was an important part of the overturning circulation or not. A few years ago, in a joint experiment with Japanese scientists and Australian scientists, we deployed some instruments along the flanks of this plateau to measure the deep ocean currents there. What we found were some surprises. The first surprise was that the ocean currents were quite strong. The average speed over 2 years was about 20 centimeters per second at a depth of 4,000 meters. So 20 centimeters per second doesn't sound very fast, but for the deep ocean it's very unusual. In fact, they're the strongest, the quickest deep currents that we've measured in the ocean at those depths. It sits about 4,000 meters below the sea surface and runs along the seafloor, but it extends for thousands of meters up through the water column. So it occupies a lot of the depth of the ocean, but it's quite narrow. It's only about 50 kilometers across. So we've used those current speed measurements and measurements of temperature and salinity of the water to calculate how much water is moving northward away from Antarctica in this deep current system. And we found that it's about 10 million cubic meters of water per second. That's a pretty tough number to get your head around. If we add up the flow of all the world's rivers combined, we get about 1 million cubic meters per second. This deep river of cold water flowing away from Antarctica is about 10 times the size of all the world's rivers combined. And so what that tells us is that this is indeed an important branch of this overturning circulation. And it's one aspect of the ocean currents that we need to understand and be able to simulate if we're going to project how climate might change in the future.
Little research has been done on the oceans of the southern hemisphere compared to those of the northern hemisphere. However, over the years, measurements of southern ocean currents have been improved through the use of innovative satellite systems.
So what's changed in the last few years is, first of all, much better satellite instruments. We have satellites that can now measure the height of the sea surface to within a millimeter or two. We're able to study ocean currents from space now in a way that we couldn't do before. It works a little bit like a speed gun that police might use on a highway to determine how fast your car is moving. It sends down a radar pulse from the satellite. It bounces off the surface of the ocean and returns to the satellite.
Argo, a robotic instrument that collects regular information on the status of ocean currents, is a collaborative international project in which 23 countries contribute floats and many others help in implementation.
It's an instrument that drifts with the ocean currents at a depth of 1,000 or 2,000 meters below the sea surface. It's carried by the ocean currents, and every 10 days it inflates a small balloon that's part of the instrument. That changes the buoyancy. It makes the float a little bit lighter in the water column, and it rises through the ocean from 2,000 meters up to the surface, and it measures temperature and salinity and sometimes oxygen levels as it goes. When it reaches the surface, it can transmit that data to us by satellite, and then sinks back down again and drifts for another 10 days. We now have more than 3,000 of these instruments deployed throughout the world oceans.
We sincerely thank you, Dr. Stephen Rintal and Professor Anders Lieberman, for taking time from your busy schedules to speak with us about the oceans and their relation to our planet's climate system. From your significant research, it is apparent that the functioning of the Great Ocean Conveyor is highly important in controlling how much carbon and heat our oceans can absorb, and thus plays a very significant role in determining the extent of future climate change. For more details on the scientists featured on today's program, please visit the following websites. Professor Anders Lieberman, www.pik-potsdam.de. Dr. Stephen Rintal, www.csiro.au. Eco-conscious viewers, thank you for joining us on today's program. Please join us again next Wednesday on Planet Earth, Our Loving Home, for the final part of this two-part series. Coming up next is enlightening entertainment after noteworthy news. May the guidance of the Providence always be with us.
For more details, please visit www.suprememastertv.com/PE